nice out there. My name is Rose Jansen. I'm with the Academy of Science St. Louis, and I'm just going to tell you a little bit about the Academy before we begin tonight. This is a Perspectives on Science History series talk. It's a partnership of the Academy of Science St. Louis and the Missouri History Museum. And so many of you are familiar with the Academy, and for those of you who aren't, we are a local nonprofit that's been serving the St. Louis community and surrounding counties since 1856, and we have a long-standing mission to advance the public understanding of science and inspire the next generation of scientists and science advocates. And we continue to celebrate more than 150 years of community service by offering a very broad range of free and low-cost public science programs, collaborative seminar series, and trips and tours that highlight science at venues throughout the region. And you can find more information on the Academy and our upcoming community-wide events and programs by visiting our website at academyofsciencestl.org. So with that said, I'd like to introduce tonight's speaker, Dr. Frank Flinn. Dr. Flinn received his undergraduate degree from Quincy College, Bachelor of Divinity, magna cum laude from Harvard Divinity School, and a Ph.D. in Special Religious Studies from St. Michael's College, University of Toronto. He is currently adjunct professor of religious studies at Washington University. His research interests, as well as courses he teaches, include the North American religious experience, religion and science, Christianity in the modern world, and cults in America. Dr. Flinn is here with us tonight to talk about one of the best-known examples of a religious and scientific clash of ideas, the famous historic conflict between Galileo and the Roman Catholic Church, and whether or not the conflict was necessary. On behalf of the Missouri History Museum and the Academy of Science St. Louis, won't you please join me in welcoming tonight's presenter, Dr. Frank Flinn.
I want to thank Rose and the Academy and the History Museum for inviting me to give this lecture. And I want to thank all of you for coming. I'm kind of astounded by the turnout, and this speaks well for St. Louis. This speaks really, really well for St. Louis. In order to understand Galileo, you have to understand what went before. And I have a shorthand for the concept of what science was like in the Middle Ages. And, I need an eraser too. Is there an eraser back up there? Or actually, paper towel would do it too. But in my class, when I teach it, I define the scientific Middle Ages as the Bible plus Aristotle plus Ptolemy. Okay? And you got to take those all things. In fact, when you read Thomas Aquinas, he is using Aristotle's metaphysical and scientific categorical sets of categories in order to interpret the Bible, and through the Bible to interpret the world. And in a certain sense, you can say the Middle Ages is defined is that the book of Scripture, okay, the book of the Bible was the way that you interpreted the book of nature, okay. And what happens over time is that you go from there to Galileo, and Galileo says, no, you got the book of the Bible, which has truth, and the book of nature. So he puts them kind of on this scale, and then finally you get into our contemporary science, and what's happening in contemporary science is that people are using the book of nature to interpret the book of the Bible. Okay, so there's been a kind of a reversal in time, over time. The other thing that's important to realize, by the way, everybody in this room is an Aristotelian, whether you know it or not, right? You don't think you are, right? Okay? And, but what did I just do here with this pencil? Right? What did I do? No, I didn't draw a line. Something happened there. What happened there? Huh? I caused quality, quantity, place, okay, place in motion, motion in rest. We got all of these categories from Aristotle. So we're still using Aristotle's categories. The real question is not that we're not Aristotelians, it's how we've modified Aristotle in the modern world. And Galileo was probably the first person, well, no, he wasn't, lots of others, the first person scientifically to do that. You have to realize that Aristotle, they had a geostatic and geocentric system. It's up there on the board if you can see it. The Earth is in the center, okay? The Earth is in the center, the sun was third out, okay? And then you have these spheres, okay, going out. And as you went from the Earth to the top, and up at the top here are the fixed stars, right? The fixed stars going around the Earth, okay? The fixed stars are, you go from imperfection, okay, and actually you go up to the moon, which goes around, you go to the moon, to perfection, okay? And the reason that everything is going around is that everything is going around in a circle. Number one, what's the nature of a circle? A circle is what? Has no beginning and no end. Therefore, a circle is a very good image for who? Huh? The big G. Okay. Okay, for God. Okay. And in fact, Aristotle defined God, you're going to learn some Greek, noesis, as noesis, noesios. Say, oh, sorry. Anyway. God is literally the circular thinking of thought itself. God is reflecting on God's self, so God is God's own final cause, and the world is moving around in circles, the whole universe, because it is imitating the deity. And the higher up you are, with the fixed stars in the heaven, right? And everybody knew they were fixed stars, or thought they were fixed stars until whom? Who discovered that they were fixed stars? You don't know? Huh? Who? I didn't hear. No. Haley. Haley read old charts, the old Arabic and Jewish and Christian medieval charts, and he compared them, compared Ptolemy's charts, and he compared them all the way up to modern time, and he realized that Arcturus had moved if the charts were accurate. So that this fixed star had moved. He was the first one to discover. Interesting. Okay, so you have this kind of system. The world is imitating God. The world is a reflection of God. In Aristotle's system, God is not the cause of the world. So Jews and Christian and Muslim theologians had certain problems with that. Okay, big problems with that. What they solved it with this notion of sempiternity, where they said that God had created the world as it is from eternity. So the world is sempiternal, created but eternally created. Okay. Nice solution, clever right. Aristotle said, and Ptolemy following him said, what you really want to do is save the appearances. Okay, and so they use this Greek phrase, sosein ta phenomena, and they wanted to save the appearances of the motion. So what they saw, the hierarchy of God, they saw this mathematical motion in circles, okay, and really what the stars were, especially the fixed stars, they were points on the circle, okay. So they were mathematical objects, okay. They were mathematical objects, and that's very important. Now, when you go to apply Ptolemy, by the way, at one time in my life, I taught Nat Sci 5, you know, at institution in Cambridge, that enemy institution. I had my students always calculate the motion of Mercury using Ptolemy and using Copernicus. And you know who comes out with the better data? Can you guess? Ptolemy does. Oh, so Ptolemy was a real scientist. We shouldn't ever see this. Ever underestimate how smart these people were. So anyway, so you were saving the phenomena, but the universe was really a mathematical imitation of God. Anyway, they thought that the sun, things arise in the east, things are moving around that way in the west, but they're not moving perfectly. Okay, and so if you in the morning, things are going around. The fixed stars are going around real regular. They don't seem to change their places until Halley comes along. Okay, but everything is motion. The sun is moving that way, but there's a little slippage. This they call the motion of the same. This is from Plato. Okay. But there was a little slippage. Now how they noticed the slippage, have people heard the notion of precession of the equinoxes? This is the dawning of the age of Aquarius. What does that mean? Anybody know? Well, if you look out on the right, you go over to Woodhenge. What is the date today? 15. 6 days from now, you go over to Woodhenge. The Woodhenge is facing due east. The sun's going to rise at that Woodhenge. Here's the hinge. It goes around circles, so you have to stand here and look out that way, right? The sun in spring equinox. Okay, the spring equinox. We're heading towards what? Okay, so it's going to rise over here. The spring equinox, the sun's going to rise, and it's going to rise, and this is the motion of the sun across, and around the sun is a band, 8 degrees either side of the motion of the sun. That's called the ecliptic. But this is the motion of the same, going the sun will go, but then over time, in fact, about 1 degree every 72 years, more or less, okay, it looks like the sun is slipping, right? So this spring equinox, the sun rose, and there was a little dot of, what constellation did it rise in? Can you guess? What's this one? This one is what? This is the dawning of the age of, this is Aquarius, and what's down there below the horizon? Anybody know? Anybody guess? That's Pisces. Okay. And there's a little bit of Pisces left. And when that finally sinks below year 2100 plus some, minus some, depending on the wall, okay, this will be below the horizon, and then you can say you're fully into the age of Aquarius. This they call the motion of the other. But also the motion of the other was used to explain another phenomenon. And if you watch a planet go across, especially the Mercury, okay, I'll do Mercury, Mars, doesn't matter. Mars will go across the sky, right? And it's moving across the sky, and it looks like it's moving this way, and then all of a sudden, bingo, it looks like it goes the other way, right? Okay, over different days. And this is called retrograde motion, and since Ptolemy said, how do I explain that? Okay, how do I explain that motion? What I do is I put the planet on a deferent circle, a bearing circle, and what happens during this period, the planet, the circle's carrying it along, but during this time when it's going backwards, this circle is moving around, so it's moving backwards, it's moving forwards. It doesn't matter which way you do this. So anyway, it explains the principle. So he not only had circles, he had equals, circles that are off of the center of the Earth, and then epicycles on top of that. And with this system, he could explain all of the phenomena. He could say the phenomena. That's the background. Is that clear? I hope it's clear, or so much. We can clarify it later. Along comes Galileo Galilei. And what we're really celebrating about Galileo Galilei, he identified him first as a mathematician, because he said the language of the book of nature is mathematics. And has he been right? I think so. Okay, he's been right. Okay. And he was first a mathematician in Padua, and then he got invited. He got invited, especially after he wrote this book, The Starry Messenger. It's called Sidereus Nuncius. Really should be called, the Star News, or News About the Stars. Okay, that's really what it meant. Okay. He comes along, he gets a hold of a Flemish, set of lenses from a guy in Flanders who was making these things. Okay, these microscopes, they were made, first they made glasses, and then they started looking at one glass to another glass, and bingo, you started getting telescopes. And he refined that and made probably the best telescope of his time, okay? But it was no more accurate than a grandpa's set of binoculars. Okay, remember grandpa's? It was about a 7 power, it was like a 7 power set of binoculars. Anyway, please, just come in. Sit anywhere. He started looking at the sky. And this starts really changing everything. Secretly, by this time, he had already embraced Copernicus' heliocentric system. Okay. He had already embraced it. But then he starts looking at the moon. Okay. And what does he see? Here's Copernicus' system. Okay. I'm going to say some more about that. He started, he saw the moon. This is one of his own drawings. Another thing he learned looking through the moon, and this is what objectors, a lot of people who objected to Copernicus' system, there was a lot of debate, even within the church, whether we're going to accept Copernicus' system. There were some people who said, well, let's accept Tycho's system. Maybe I'll show you a bit of Tycho, but boy, that'll just really confuse matters, because he's got this weird system. Okay. But anyway, or Ptolemy's system. There was actually a debate still going on among religious people and non-religious people, but among all people. The debate was going back and forth all the time. But anyway, one of the objections was you could, he learned that Venus, had really, really big time phases. Here's his drawings. Okay, look under the Ptolemy system. See, what do you notice under the Ptolemaic system? What do you see there? People looking at it? Can you see it clearly? The phases of the Venus are pretty much the same. But he gets his telescope out and he says, look, if I put the sun in the center and the Earth over here, and I look at Venus, oops. That's where we are tonight. If I look at Venus, I see these distinct, Venus has phases exactly like what? The moon. And it works better, and my telescope tells me it's better if I accept heliocentric motion. And then my favorite one is, he said, Saturn has ears. Of course, he was seeing what? He was seeing the rings. Okay. He said Saturn had ears. It was my favorite. I love those whole things. Okay. He knew they weren't ears, but that's what they look like. They look, they look like this. His drawings of them, unfortunately, I didn't get one up, but his drawings of them were like, he had Saturn, and he had ears. Floppy Mickey Mouse. And he saw some of the rings, okay? He saw them. Maybe that's where Mickey Mouse is. Then he saw something that was really important. Big time important. Big time important. He went out and of course, you people know that Galileo died blind. Are people aware of that? And you know why he got blind? He started looking at the sun, which was darn telescope. But he noticed the sun was out there, and this really blows the water out of the Ptolemaic sun. If anything was supposed to be perfect, the sun was supposed to be perfect, the source of heat and life. And he started tracking the sun, and he would see a spot here. And then, a few days later, the sun has a cycle of about a month, right? And then he would see it a few days later, and then a few days later, and a few days later, and a few days later. And not only was the sun, imperfect, but the sun was in motion and very likely turning, as the earth was, on its own axis. And that's a big time. That's a big time. He publishes this. He starts speaking in favor of the Copernican system. The church intervenes in 1616. By 1616, says Galileo. The church says, okay, we're going to follow the Aristotelian rules. Okay. And the number one Aristotelian rule with phenomena was save the phenomenon. One. Second rule was you can use any system in the world. You can use Tycho. There were people in the Vatican who liked Tycho a lot. Okay. You can use Tycho. You can use Ptolemy. You can even use Copernicus. Okay. But you can only hold other theories other than Ptolemy suppositionally. Big word. Supposition. You can only hold it as a supposition in order to explain the phenomenon. You couldn't say this is the way the world really is. So he was put under this restriction. Okay, he was put under this restriction beginning about 1660 by the Inquisition. Okay. Now I could do a whole history of the Inquisition. That would take me hours. Suffice it to say, it started in Spain, spread to the Vatican. Okay. During the the Council of Trent, and interestingly enough, the very first book to be put on the index was written by a cardinal. It's very a book called De Emendanda Ecclesiae on correcting the errors of the church. by a very pious, one of the founders of the Oratorians. Okay, very pious person. This went along. He was pretty safe. And then he decided, he befriended this guy named Matteo Barberini, who became the Cardinal Archbishop of Florence. Okay. And then Matteo gets elected. And he took the name of Urban VIII. And I think Galileo, and by the way, let me say this, Galileo was not known for his modesty. If he thought he was correct, you knew it. Okay, he was not, some people say he's a man after my own heart. Anyway, he was not modest. But anyway, he said, hey, maybe I can get away with it. And so he wrote this dialogue, the dialogue of the two world system. And he wrote the dialogue with 3 characters. The first one is named Salviati, named after a friend whose name was Salviati. What does that word mean? Anybody know? Guess it? Huh? Saved. Next one was Sagredo. He was the god. Salviati was expounding, can you guess whose system? Yeah, Copernicus. Okay, and then he had this other character he called Simplicio. Okay, and you know whose system he expounded, right? Can you guess? And Sagredo, it's a straw dog argument, by the way. Sagredo oscillates between the two, but he oscillates kind of this way. You know? It's really clear. It's really clear. And so they argue for and against it. Extremely well written. It's a piece of literature. Okay. But he made one big fatal error in it. Did you know that? You know about Galileo's error. You never heard about Galileo's big error. What was his big error? Anybody? He thought that the earth was moving, it was whirling around, and going around the sun, and whirling on its own axis, and that was causing what? To go up and go down. The tides. Okay. And he thought that was one of the arguments for the earth moving, were the tides. He got corrected by whom? Johannes Kepler. For some reason, he didn't get along with Kepler. The Copernican system is still a circular system. Kepler is the one who found out what? That they move in ellipses. Anyway, but that's another lecture. That's a whole other lecture. Anyway, so he has this thing, and then people inside the Vatican, he actually has him quote people. He has these quotations from him, and some of these, they're not exact, but they sure look like Urban VIII. Now, whether this is true or not, I've never really decided. Okay, I've never really decided. But they look like Urban VIII quotes stuck in the mouth of the simpleton. Okay? And so, they go, people inside the Vatican saying, wait, boy, look what he's doing. He's giving you the shaft. And so it gets called before the Inquisition. Okay? And they, as he's being tried, they haul in the instruments of torture. Let him know this was serious business. and it goes back and forth. Okay? Goes back and forth. And it ends up with, in a certain sense, some people say it was an intellectual tragedy, and it is, okay? Where he says, I abjure Copernicus' system, that it's full of error and all of that, okay? And then he was sent home to house arrest in Florence. But, everybody sees this as a tragic end, but it wasn't, because what he did when he went home is he gathered up all these notes and all these experiments he did with motion and in-kind planes, and he worked out the laws of acceleration and the laws of inertia and all of this other stuff. And that's what set the real stage for who? Mr. Newton. So it wasn't a wasted end of life. He was very creative. The book Galileo's Daughter really portrays that very, very nicely. The objections the church had to the Copernican system was, number one, they said, well, if this is true, then God created a world that's deceiving our senses. And what kind of God is that? Think of that, right? Think of that. That's given the times, that was a kind of a valid argument. And the second objection was the appearance of Venus's phases. He said they don't seem to be marked. Of course, he handled that one already, right, in 1610 with the telescope. And then the next one was the objection said, well, Mars should be a lot brighter than you say it is. Well, interestingly enough, the telescope did show that Mars was a lot brighter, okay, when it was closer and further away. Okay. And then one of the biggest arguments was parallax. Big argument. Here's the sun. Say we're going to assume Copernicus system. Here's the Earth going around it, right? The distance between the Earth and the sun is what? What do we call that now? In AU, right? Astronomical unit. Circa 93 million miles. And they said, his opponent said, well, if I took a fixed star and I measured it in the winter, and then I measured it in the summer, I should see what? What should I see? I should see a big angle. Now, it was a very legitimate argument. What's the problem with it?
Stars so far away.
This is the whole solar system right there, right? And where's that fixed star? Huh? Where is it? The nearest fixed star is what? How many light years? 4 light years away. Way up there. And, draw the angle there. I'm going to move that over to here. Here's the angle, right? There is no angle. Until you have a really sophisticated telescope, set of instruments. You need really sophisticated. And this problem was not solved. It was a legitimate objection. It wasn't solved until 1838. It took a long time to solve that. So that was one of the objections. And then, the objection I'm going to demonstrate tonight, we're going to do a scientific experiment. And they said, well, I'll do both of them. They're both of the same quality. They said, well, if the Earth is moving and I shoot a cannonball in the direction of the motion of the Earth, and the opposite of motion of the Earth at the same time, right? Then the cannonball in the motion of the Earth, one should be shorter than the other, right? Okay. Does that happen? Do you think it happened? Why? Depends on the second one. Second argument is they said, well, if the Earth is moving and I'm sailing on a boat, and I drop something from the mast, right? The boat should keep sailing so it should fall behind, right? And this is where Galileo starts becoming new, because he says, no, that's not how it's working. What is happening is that the ball in my hand is going to participate in my motion, and watch the way the ball's going to move when I drop it, okay? I'm not throwing it, I'm just going to drop it. Which way did that ball go? Huh? It went this way, right? Why? What do we call that now? Conservation of, okay, momentum. Part of, and Newton's going to take that up, that's conservation of energy. Okay, the carbon subset of conservation of energy. That was a brilliant answer, and it showed you something about him. Galileo answered his enemies. By the way, none of the people inside the Vatican, except with parallax, and I give them credit for that, went out and ran tests. What's it called? Rejection prior to inspection, or very interesting way to approach the world. And I think that where Galileo's genius where the church made an error was the church didn't see what was really going on in science. It wasn't following science. It was kind of distancing itself in the Roman Catholic Church at this time was being buffeted by the waves of Protestant. You know, the 30 Years' War was, the wars were around just around the corner and being buffeted. And even though Urban Matteo Barberini had been a friend of Galileo, and Galileo had explained to him in the Vatican Garden the entire Copernican system, and he was even sympathetic to it, he felt himself forced to condemn. Was the condemnation necessary? There's a professor at the University of Chicago, gave a lecture here at WashU a few years ago, and he claimed that had Galileo not been so arrogant, he could have finessed it. I don't know. I personally do not know. What I do know, though, is that Galileo changed the way we are in the world and the way we perceive ourselves in the world. Number one, and he did it, I call them my Galilean conclusions. He says he realized that the universe was it's one universe, and it's the same throughout. What's going on in the sun can be related to what's going on in the moon and what's going on in the earth. The sun may be, there's some different things going on, but it's one universe, and you explain it with one set of mathematical laws. Second thing is the world is physical, okay? You have to take account of the physical. The stars aren't moving because they're on circles imitating a thinking thinker, okay? The stars are physical bodies being physically moved through space. So the world is a physical place. And like Ptolemy, he agreed with Ptolemy here, it's mathematical, okay? But it's a mathematics of the physical, not a mathematics of the theoretical. Okay? It's not theoretical mathematics, it's physical mathematics. And then finally the universe is mechanical. Okay? It's physical and mechanical, and you can find laws to describe it. And that's what he did at the end of his life. He went out and found more laws. Okay? It wasn't a waste of time. He got a lot of help from his daughter at the end, who was always, by the way, Galileo was the pious person in his entire life. There is some story that when he finally abjured the Copernican system, as he was being let out of the room, he said under his breath, "Equor se muove." Nonetheless, it still moves. Thank you. Any questions? Any questions? Yes.
You mentioned that the church is not following science at this time, and I disagree with that a little bit because, especially the Jesuits were tremendous in science in this time. In the 16th
No, I'm saying the Vatican. When I said the Vatican, I mean the official church.
The 1610 business with the Jesuit college,
Right.
and they greeted him enthusiastically.
Right.
And Urban VIII was his main sponsor and encouraged him to write the diary.
Right, that's right. He was encouraged.
The Pope encouraged him.
Yes, the Pope did. But by the time the trial happened, the church was concerned about other matters than scientific
Well,
matters.
he agreed that he would treat Copernicus as a hypothesis.
Yeah.
He came away from his promise. Now later, of course, he was right.
Well, when you read the dialogues, it's an hypothesis, but it's still right.
That's
It's
true.
still really, they under the breath thing. Yes.
I was wondering whether you have any idea about the truth of something I've heard, that Galileo tried to measure the speed of light, but he was convinced that sound was instantaneous, and so the various experiments yielded a very crazy solution.
There were people talking about doing that, and there were some experiments, but I don't know that he really engaged in that very much. Okay. There was talk. Okay. I don't know your answer, I have to go and research. Good question.
Has Hubble modified into the Galilean conclusions on universal, physical, mathematical, mechanical uniform?
Who did?
Hubble, the
Hubble,
the
yeah.
findings of Hubble, have they
Yeah.
modified into the Galilean conclusions?
Well, I mean, there's, no, not whatsoever. Okay. Galileo, I mean, you draw a great, especially with the later, when you've got the laws of acceleration and momentum and conservation of energy, you know, you start approaching, you right up to the door of Newton, and you just go right in, okay? Now, Newton is not even undone in relativity, right? Newton applies in the macro world, right? We didn't need Einstein to send, we don't need Einstein to send the Atlanta stuff, right? All we need is Newton, okay? So within this system, Newton applies fully, but when you get into the subatomic realm, something else is going on there. And I think total ignorance. Near total ignorance. Yeah.
Were the church fathers aware that the world was spherical around, or was that,
No, by that time, everybody had been convinced, okay, they listened to enough sailors. Why do you use the sailor argument? Well, if you look at the ship going off in the horizon, right, it doesn't get smaller and smaller, it gets, you don't see the, you know, finally you're just seeing the top sail, right? Draw your conclusion. Bingo, it had to be curved to that. Yes, Doctor?
A personal question, if I may. The more learned you become, how does that affect your...
The more what?
The more learned you become, how
Some people don't use that adjective about me.
how does that affect your view of the universe?
Oh, listen, you know, I have no trouble with my faith in I think the universe just gets more and more mysterious. You know, it's profoundly, you know, the more we know, the more we don't know. Okay. And, you know, I'm all excited about, you know, I'm really excited that there may be multiple worlds, right? Multiple universes, you know. I'm now telling my students don't commit suicide. It's a waste of time. According to Max Tegmark, 4 to 10 to the 28 meters from here, there's an identical view. Okay. And there's another one, ad infinitum. Okay, so it's a useless to commit suicide.